Hello friends, welcome to a quiet voyage through dust, distance, and discovery. Tonight, we drift toward a world that looks utterly still, a cold, rusted desert circling under a smaller, paler Sunday. From here, it seems lifeless. No forests, no oceans, no echo of breath, only a faded red dot wrapped in silence. But that silence lies. Because when NASA's rovers rolled across that emptiness, Mars began to whisper back, not with sound but through shadows, patterns, and glimmers buried beneath its dust. And what they found there will truly surprise you. Observations so strange, so unexpected, that even seasoned scientists had to question their own assumptions about this world. So tonight, we'll unfold those discoveries slowly, one layer at a time, each small detail revealing something the eye alone could never see. Not to rush, not to lecture, but to let you feel how Mars speaks, quietly, through its light, its air, its endless waiting. A thin hush falls over a rusted horizon, like a breath held before sleep. Mars waits without hurry. Its surface glows with iron oxides, tiny grains that scatter sunlight into copper noon and soft salmon dusk. The planet's day is familiar yet just beyond reach. One sol lasts about 24 hours, and 40 minutes a quiet surplus that slows the clock's tick and gives evening time to lengthen. At certain twilights, the sky performs an inversion of Earth's palette. When the sun sinks low, fine dust favors blue light forward, and sunsets can turn azure near the sun, while the rest of the sky keeps its pale warmth. It is simple scattering at heart, but from the ground, it looks as if the world is gently exhaling color in reverse. If this calm journey into the red horizon brings you wonder or peace, let it travel further. Like, share, and subscribe, so this quiet exploration can reach others, drifting under the same sky, who might need a slower kind of science tonight. A low ring of battered rims steadies the northern flats, where plains widen into old lava and fine, restless dust. Through a telescope, the planet holds a familiar poise because its spin and lean echo our own. The axis tilts close to 25 degrees, enough to draw out quarters we also name spring, summer, autumn, and winter. One turn takes a little longer than a day at home, about 40 extra minutes that slide quietly into every schedule. With that lean, winter air settles onto the cold pole as carbon dioxide, frost, and slab, and in spring it returns to the sky. Pressure rises and falls with this breath, yet the whole envelope remains thin, near 600 pascals on average, roughly 1% of sea level Earth. Winds can whistle across open ground, but the push is light. What they move most easily are tiny grains, already charged by sunlight and contact. Dust lifts, not because the air is dense, but because the particles are eager to go. When lifting begins in one valley, it can seed another. Local plumes sometimes merge into wide veils, and those veils can wrap the globe. Suspended grains absorb sunlight high above and leave the ground cooler below. In the great event of 2018, daylight fell so far that the solar-driven rover, Opportunity, could not store enough energy to wake again. That loss did not come from burial. Storms do not drown mountains. They coat, they scour, they settle in lulls and vanish in gusts, revealing dark rock in one place and painting another with pale powder. Between veils, the horizon sharpens. Cameras resolve terraces of layered mesas and the abrupt edges of valles marineris, a system that runs for more than 4,000 kilometers across the highland. From orbit, spectrometers read colors as chemistry clays, where waters once rested at neutral conditions, sulfates where evaporation and acidity grew, carbonates where carbon dioxide met basalt and locked away. Each family forms under strict rules, so a map of minerals becomes a proplake. map of former climates. Gravity softens here. A surface pull near 38% of Earth changes how grains hop, how slopes fail, how dunes breathe. Dry sediment can cascade down crater walls in thin sheets, leaving dark streaks that gradually fade as new dust settles and brightens the surface again. For years, recurring slope lineae were suspected to be briny seeps, but sharper imaging and thermal behavior pointed many of them toward dry avalanches, triggered by seasonal heating and wind. That difference matters. Persistent brines at the surface would require salts to hold liquid in cold, thin air. Dry slides ask only physics and sun-warmed facets. The debate continues with care, balancing temperature ranges, humidity limits, and the chemistry of salts against the patterns of timing and slope. The patient habit here is comparison, again and again, until one explanation fits more angles than the others. Above and below, this world carries a long memory. The crust holds basaltic plains, impact basins, and sedimentary stacks. Under that lies a mantle and a core whose cooling pace altered the sky. Ancient lavas record remanent magnetization in narrow bands and scattered blocks, proof that a global dynamo once operated. Today, there is no planetary shield. The solar wind can interact directly with the upper air, and instruments have measured the loss of lighter atoms to space. Over billions of years, that escape, joined with internal cooling, thinned a once thicker blanket. With less greenhouse warmth, rivers dwindled, lakes retreated, and water shifted into polar caps, buried ice, and transient vapor that now traces a smaller, colder cycle. The climate did not stop. It slowed until change could be read in layers rather than in floods. Seasonality still writes its script. Each winter, polar hood clouds form over the cold cap, thin and pale, then clear as sunlight returns and carbon dioxide sublimates. Pressure tides pulse daily as the ground warms by day and cools. By night, raising and lowering air by small but measurable amounts. These tides organize winds that climb slopes at noon and fall back after dusk, steering dust into lanes and setting ripples along dune faces. In such air, sand transport starts at higher gust speeds than on Earth, but can continue at lower values once grains are moving, because impacts free neighbors in small chains. The result is a landscape where ripples migrate centimeters to meters each year, slow enough for a rover to plan paths, fast enough to reshape the skin within a human lifetime. Clarity comes from instruments tuned to that restraint. Orbital cameras trace the retreat of seasonal caps, the spread and decay of storm canopies, the fresh scars of small impacts that excavate bright patches and then fade. Spectrometers discriminate between iron oxides, hydrated clays, and sulfate beds, assigning each a banded signature. Laser altimeters have already given the globe its measured relief, confirming the great dichotomy between southern highlands and smoother northern lowlands. Ground missions tie these views to textures under wheels and drills. Brittle crust over powder, cemented nodules in crossbeds, mudstones that break in chips and hold minerals that form only in water of certain chemistry. Each observation slots into a larger grid until the picture no longer relies on guesswork. Though the air is meager, it remains an engine. Pressure in the deepest basins stands slightly higher than on adjacent plateaus, shifting boiling points by small margins and shaping breezes along scarps. Over the course of a year, tens of trillions of kilograms of carbon dioxide move between pole and sky, enough to alter the total pressure by about a quarter between extremes. This swing changes how radiation warms the column, how waves travel, how dust lofts and settles. It is a system of delicate volumes, but its reach is wide. Even a thin blanket can carry heat and momentum across a hemisphere when the ground beneath is open and the horizon is far. If numbers seem spare, they are the right size for sleep. 25 degrees and 4 seasons, one extra slice of time in every soul. 1% of sea level pressure as a quiet boundary for what can persist in the open. 4,000 kilometers of canyon, written by long, complicated forces. 38% of Earth's pull to change the fall of a grain. These values do not crowd the mind, they anchor it. They are close enough to ours to feel known, far enough to remind us that difference can be gentle. Like a slow heartbeat heard through a wall, the planet keeps pace without hurry. In all this, there is a steady comfort. The face feels constant, not because nothing moves, but because motion has slowed into handwriting we can trace. Dust rises and rests. Frost comes and goes. Rock keeps its layers. Air takes its time. And as the hush deepens, another thought draws near, as if evening itself were lengthening by a small, kind measure, inviting us to listen to how a longer day feels when the sky grows quiet. The Martian evening lingers a little longer than ours, a rhythm we've already met before. That small surplus slides into every plan. Mission teams ease their clocks to match it during early operations, letting each Earth day begin about 40 minutes later than the one before. Sleep schedules creep across the calendar until bodies protest. When circadian rhythms fray, the teams return to terrestrial hours. But the instruments keep listening to the planet's slower pulse. The clock on Mars is not a theory. It is a shift you can feel in the bones of a plan. As the tide shifts, surface temperatures follow this longer cadence with calm steadiness. The air is thin and cannot hold warmth for long. Daylight lifts the ground above freezing for a short spell. Then the heat escapes quickly into the open sky. At night, the same place sinks far below zero, the fall sharper than on Earth because there is little air to slow it. Thermal inertia divides the landscape by memory. Rock cools slowly, dust forgets at once. Buried ice breathes in its own rhythm. Instruments trace those patterns like quiet heartbeats beneath stone. Another lantern appears when infrared eyes scan the plane. Orbital sensors and rover cameras translate nightly swings into maps of grain size and rock abundance. Coarser ground glows longer after sunset. Fine dust fades first. Contours of temperature reveal hidden crusts and old beds, clues to where salts or ash may sleep. These maps become road signs. A rover may choose the firmer route, the safer ridge, the mixture of grains that might cradle ancient organics. And still, the night continues, carrying a sunset that looks backward to our intuition. Dust grains, barely a micrometer wide, scatter blue light forward near the sinking Sunday. Red lingers in the wider dome, but the halo around the disk turns cool for a moment before the copper glow returns. It is not artistry, but thin physics. The way light walks farther through rare air and shows its path before it fades. For a few breaths, the sky seems to reverse itself. Blue where warmth should live, rust where day retreats. At dawn, the page turns the other way. Slopes facing the first light brighten, and faint frost begins to vanish. On high volcanoes near the equator, morning frost forms in colder seasons, films only microns thick, yet spread across broad calderas. They melt to vapor within minutes, feeding a trace of humidity that drifts downslope. Each cycle is delicate but cumulative, part of the slow breathing that still ties air and ground together. Another rhythm, quieter but planetary, moves through pressure each sol. Carbon dioxide freezes onto the winter pole and returns with spring sunlight. Global pressure rises and falls with this frozen breath, and upon it ride thermal tides waves driven by day-night heating that circle the planet like invisible surf. Barometers feel their arrival. The pattern repeats with the sun, reliable as a pulse written in millibars. As noon's lantern passes, rovers sense these murmurs. Tiny sensors twitch with each tide, winds reverse as slopes cool, and dust lifts in soft saltation. Engineers fold these signs into careful plans, drilling when breezes calm, moving masts before gusts, saving heater power for the colder phase to come. Every watt and minute belongs to the atmosphere's rhythm. Another lantern glows in the schedule itself. That extra 40 minutes per sol slowly shifts communications, pushing link times across Earth's nights. When Mars drifts behind the Sun, the line goes silent for days. When geometry favors closeness, the delay shortens and energy flows steadier. Operations stretch and contract like breath, an unseen synchronization between two worlds. Energy sets the limit for every act. Solar panels tilt, gather, and lose. Dust dulls them. Wind sometimes clears them, but never by command. Batteries warm themselves against the cold. Power flows where it must into motion, into heat, into patience. The best hour for a panorama is not only the beautiful light, it is the moment when charge and calm coexist. Another lantern, softer, is the way light writes shadows. Tracks lengthen a little more each evening, their edges drawn thinner by the slower spin. Twilight lingers long enough for stereo images with less glare. Navigation gains depth, science gains calm. Small advantages, multiplied across months, become safety and knowledge. As the night closes, patience becomes its own science. Mars does not hurry you. It asks for care measured in minutes and watts, for attention that moves with the rhythm of frost and dusk. Data arrives like breaths, images at all hours, spectra tracing frost at dawn, pressures rising and falling with the thermal tide, radiation ticking through quiet afternoons. Each line adds to the portrait of a world that reveals itself gently, a little slower, a little longer, inviting us to match our breath to its turning. Low sun tilts toward the plain, and the air begins to reshape light. At shallow angles, dust becomes a soft lens, not glass but suspended grains arranged by wind and height. Forward scattering gathers near the sun, focusing blue toward the eye while the wider dome keeps to red. The halo is narrow, close to the source, a rim of cool brightness around a sinking star. Elsewhere, longer wavelengths travel farther and warm the sky into rust and gold. It looks effortless, yet it's born from geometry and grain size, tiny spheres bending light until evening glows like memory itself. The air's thickness to sunlight has a number the watchers know. Tau, the measure of optical depth. Low tau means a clearer path, strong shadows, panels drinking light. High tau dims the ground, cools the soil, softens every edge. During regional storms, the number can climb in leaps. Horizons fade into amber, and distance slides away. Cameras respond with longer exposures. Solar arrays surrender watts they cannot catch. Routines compress. Fewer drives, longer rest, and every scientist takes note because each decimal of tau holds inside it the planet's balance of warmth and work. Dust does not only scatter, it stores the day. Suspended grains heat the middle atmosphere, a band high above the rocks. That warmth shifts pressure and gives birth to thermal tides that circle the world. They pass overhead like unseen surf, raising and lowering surface pressure with dependable rhythm. On the ground, instruments feel the sway as a tiny pulse, the faint exhale of a living sky. When dust thickens, a quiet inversion settles warm air above, cold trapped below. Turbulence eases, noise dies, and the air flows in slow sheets down familiar slopes. Even then, movement never fully stops. On the leeward faces of ridges, the wind finds play. Dust devils rise in translucent columns, twisting with grace and persistence. They lift fine grains and scatter them anew across the plain. Sometimes they sweep a rover's deck clean, raising power for a day. Sometimes they etch dark paths through bright dust, tracing their dance like handwriting across stone. The pattern repeats each season, fewer in cold mornings, many under warm afternoons, and the land remembers every spiral until storms draw a new veil. In that same thin air, water ice joins the dust. Humidity is low but never zero, and motion weaves its design. Where air rises and cools, tiny crystals assemble into cirrus-like veils that drift at altitude. Morning builds them over volcanoes and canyon rims. They form, glimmer, and dissolve as temperature and saturation shift by narrow margins. Each one is proof that the water cycle persists here, not grand, but faithful. Season by season, orbiters map these belts of cloudiness and their habits. Occultation data traces vapor with height, showing where it pools and where it thins. A pattern emerges, repeating like the tides of a quiet sea. Near the equatorial highlands, dawn leaves another gentle mark. Under certain winds and cooling rates, frost grows before sunrise, a deposit measured in hundredths of a millimeter, yet spread for hundreds of square kilometers. Soil and rock turn pale for an hour, then the sun lifts, the balance flips, and the vapor slips free. By mid-morning it is gone, leaving only brightness and a line in the log. Such transient frost is a whisper of exchange between ground and sky, small in mass, immense in meaning. During dusty weeks, optics feel the touch of settling grains. A thin film collects on windows and detectors, subtle but decisive. Teams respond with ritual care. Lamps flare, filters slide, reference targets shine. Calibration resets color and focus so spectra stay true. The routine repeats after storms or days of stillness, because even gentle settling builds up season by season. To keep the science honest is to keep the ritual alive. Spectrometers read composition through light's behavior. Dust enriched in nanophase iron darkens certain bands, absorbing warmth and shaping the color of day. Ice aerosols do the opposite, reflecting well and etching subtle signatures in near-infrared spectra. Cameras with calibrated filters trace these changes hour by hour as storms rise and decay. Temperature and pressure logs add their notes, and models translate them into grain sizes and settling rates a day to clear when heavy, a week when fine, longer if the air stays stirred. From these rhythms, the atmosphere gains its portrait, a system sparse but alive. As the light thins, the blue halo returns. It is more than beauty, it is measurement made visible. The forward scattered glow tells how high dust has risen and how long it will linger. It whispers of radiative heating aloft, of pressure tides and the balance between calm and motion. To see it is to read physics in color, a spectrum made emotional by distance. Another lantern follows in the chain. Warm air above keeps lower gusts. Gentle air lets frost settle where cold creeps. Morning clouds ride those paths like soft banners over ridges. Each process feeds the next. A devil cleans a panel, the panel powers a camera, the camera captures iron that colored the dust in the first place. The loop closes quietly and opens again each day. And still, the night continues with its patient exchanges. Tau will fall after the storm and rise with another season. Cameras adjust, arrays recover, frost visits and vanishes. The blue edge sharpens, fades, and returns. Each cycle marks the heartbeat of a thin but faithful sky, one that connects dust and light, ground and mind, in a conversation as slow as the planet's turning. Across basins and the calm floors of old craters, ergs gather like a resting ocean of grains. Dune fields ease across the ground in broad sheets, shaped by prevailing winds into crescent barchans. with horns stretched downwind, into multi-armed star dunes where directions have shifted, and into long transverse ridges that track a steadier flow. Grain sizes fall mostly in the realm of fine to medium sand, simple and familiar, yet their motion answers rules that differ from home. Gravity is weaker, yes, but the air is thin, so the threshold for motion rises. The stage looks gentle, while the start of movement asks for surprising force. Saltation remains the main choreography. Grains lift, arc, and return in short hops that strike neighbors. To initiate that dance, winds must reach higher speeds than Earth would ask. But once grains are aloft, modest breezes sustain the flow because each impact knocks others loose. It is a quiet relay, one leap nudging the next. Engineers sum it plainly. Initiation demands strength, continuation accepts less. That difference explains active streaks that awaken in brief gusts and then glide on softer air for a while longer than instinct expects. As the tide shifts, ripples write those thresholds into form. Rovers have photographed low ripples with short wavelengths and modest heights that fit today's atmosphere, and beside them larger mega-ripples whose wider spacing hints at earlier, more energetic conditions. The surface reads as a bimodal script, two scales sharing one bed. The smaller pattern likely grows under present winds. The larger bodies endure, their crests trimmed at the edges as modern grains nibble at old architecture. This contrast is useful, a compact record of air power and grain supply left in place. Tracks over these surfaces speak of slip, sinkage, and recovery. On slopes of only a few degrees in fine sand, wheels can drift downslope while pointing straight, a subtle lateral slide that calls for low speeds and gentle steering. When ripples run perpendicular to the planned route, burying risk rises as crests collapse under weight and troughs stall momentum. Navigation teams weigh science targets against traction every day, choosing paths that keep the vehicle moving while still touching the right rocks. Avoiding just a few unfavorable angles can preserve margin, and a short detour on firmer ground often returns more science than a stubborn push. Another lantern appears beneath the skin when ground-penetrating radar looks through the dune bodies. Subsurface echoes trace crossbeds that dip at angles, the signature of former slip faces migrating over time. Inverse grading captures gusts where heavier grains arrived later in a pulse. Thin silt sheets lie between sand sets, reminders of quiet intervals when dust crowded the air and settled out. These units record changes in wind regime, directions that swung with seasons, strengths that rose and fell with supply, and pauses when fine dust choked movement. Where dunes mantle older, cemented surfaces, the radar contrasts loose layers with indurated crust below. Drills confirm that contrast. Bites into loose sand go easily, the auger advancing with little resistance, and then a firm refusal greets the tool at the crusted substrate. That indurated layer can be a cement of salts or silica, a stubborn floor under the mobile cover. Such two-story ground simplifies sampling decisions and also anchors dunes that would otherwise drift farther. It is a quiet foundation, shaped in past moisture or vapor episodes, now serving as a break on the present sea. Composition mirrors the sources. Near volcanic provinces, dark dunes carry basaltic grains that keep their color and toughness. Lighter-toned fields include altered fragments, sulfate grains that point to fluid pathways, and glass shards forged in heat and shock. Chemical instruments taste coatings of oxidized iron that give the familiar red and detect perchlorate salts that matter for water and for work. Perchlorates lower the freezing point of brines, welcoming brief liquid films in cold shadows. Yet they complicate life detection because heating can drive reactions that oxidize organics. In planning future resource use, Those salts promise help and hazard in the same breath. In the thin, dry air, grains develop static charge. Contacts and separations during saltation build tiny imbalances that promote adhesion to housings and may assist dust lifting in turbulent gusts or dust devils. Electrostatic cling is a small, persistent factor, answered by brushes, covers, and careful scheduling. It belongs to the same climate that makes starts difficult and flights long once they begin, a setting where every collision matters a little more. Under such constraints, the physics stays friendly. Rounded grains, simple hops, energy tallied in short exchanges. Dunes breathe with the seasons. In winter, carbon dioxide frost binds the upper centimeters, stiffening faces and locking crests. In spring, sublimation unfastens the bonds, sometimes destabilizing slopes and triggering small slides that refresh scarps. Repeat imaging shows migration from centimeters to meters per year, depending on locale, exposure, and grain size. The pace is slow enough for safe driving and fast enough to renew surfaces within decades. Along crater rims, perched dunes testify to winds channeled by topography. In the lowlands, broad fields align with regional flows and curve around bedrock promontories like water around a pier. And still, the night continues across this quiet sea, where patterns double as archive. Orientation speaks to direction. Height and spacing register energy. Star nodes mark variability. Crossbeds and silt partings preserve episodes when winds shifted or dust drowned motion. The map is not decorative. It is the climate set into sand that remembers. As a rover pauses on a ridge to test the air and taste a grain, the broader story waits in the lines beneath, ready to guide the next valley crossing when morning returns. Olympus Mons rises higher than most clouds could dream, a shield volcano standing about 22 kilometers above the surrounding plains. Its slopes are broad and gentle, tilting only a few degrees for hundreds of kilometers, and the crest is broken by a caldera complex that sprawls for tens of kilometers. The flanks carry the quiet signatures of time, lobed tongues of basaltic lava, sagging collapse scars, and soft wrinkle ridges that crease the ground. Each feature marks an eruption or a pause, a pressure released or a chamber emptied, the record of activity repeating across long Martian ages. The mountain's immense size follows simple physics shaped by a different world. Mars pulls less strongly than Earth, so buoyant plumes can stack thicker piles before they spread. Its crust bends under weight in another way, redistributing the load so the edifice can keep growing rather than sinking. In the Tharsis region, where Olympus Mons stands with other great shields, the crust rose as a vast uplift. Radial graben cut outward like spokes, signs that the mantle once convected with vigor and fed widespread magmatism. The result is a plateau of giants, each built layer by layer, flow by flow, until the highest peak surpassed ordinary weather. Near the summit, the air is thin to the edge of breathlessness, and temperatures swing sharply with day and night. Radiative forcing rules here, because the atmosphere carries little heat. As morning light returns, surfaces warm fast. As evening falls, they cool as quickly. Orographic clouds often gather against the highlands, the way a gentle wave curls over a sandbar. At dawn, in certain seasons, a film of water frost forms on the tallest volcanoes, including Olympus Mons. The deposits are delicate, only a few grains thick, and they evaporate soon after sunrise. Yet the summit is broad, and when a thin layer spreads over a large area, the total mass added to the seasonal cycle is not trivial. The process links shape to climate. Nighttime cooling drives the air toward saturation. Upslope winds concentrate moisture at altitude. Tiny crystals grow where the temperature briefly dips below the dew point. Sunlight then returns, and the frost turns directly back to vapor. This is not snowfall or rain as we know it. It is a daily exchange between vapor and solid, a reversible handshake controlled by slope, height, and chill. The mountain, by being high, becomes part of the current Martian water cycle. Modest in quantity, patient in rhythm, reliable as breath. The rocks that built Olympus Mons are dominantly basalt. Basalt carries iron and magnesium, and it flows easily when hot, spreading in sheets that cool to dark plains and smooth ramps. Over time, the same chemistry repeats, so the volcano grows wide. Yet even basalt can change where water and heat meet. On Earth, eruptions trapped beneath ice make glassy fragments called hyaloclastites and weather them into palagonite. On Mars, past lava may have intersected ground ice or buried icy soil. Where that happened, hot rock could have melted pockets, driven hydrothermal circulation, and created brief environments with liquid water and chemical gradients. Those are the simple ingredients most biologists seek when they speak of habitability. Orbital spectroscopy has mapped hydrated minerals downwind and downslope from volcanic centers, subtle fingerprints of past alteration. The challenge is context. Some signatures may come from dust, or from older layers exposed by erosion, or from groundwater rising and evaporating. High-resolution images help by revealing textures. Scalloped margins suggest flow fronts that collapsed onto softer ground. Pit chains hint at voids below. Skylights puncture some lava tubes, offering portals into dark corridors that may preserve steady temperatures and shield against radiation. Future explorers could use such tunnels as shelters. In a place where the surface swings widely in cold and is bathed in energetic particles, a stable subsurface chamber is practical, not romantic, like a quiet room under a noisy roof. The caldera at the top is not a simple bowl. It is a nested series of pits and terraces, each one a note in a longer song. When magma withdraws from a chamber, the roof can fail and sink, leaving concentric faults and steep walls. The arrangement at Olympus Mons tells of stages rather than a single collapse, a sequence in which chambers filled and drained, rose and sagged, and changed size with time. The landscape keeps the geometry so plainly that even a soft gaze understands the pattern. It is an archive written in circles and steps. Across the wider Tharsis rise, other clues point to the deep engine. Gravity data imply that crust thickened under the region, consistent with long-lived upwelling and loading. Global fractures align with the stress of uplift and the weight of tall mountains. The entire province looks like a frozen diagram of forces, pushing upward and outward, then cracking the cold skin as the bulge grew. The age of the most recent flows matters for the story of interior heat. Many plains and cones on Mars are ancient, but parts of Tharsis hold lava that appears only tens of millions of years old. In planetary time, that is fresh. It suggests the planet has not gone entirely silent. The mantle may be cooler than it once was, and melt may be scarce, yet the system can still find ways to leak energy. Remote sensing sees the surfaces well, but it cannot hear the faint tremors below. For that, landers listen. Seismic instruments have detected Marsquakes, driven by crustal stress, by thermal contraction, and perhaps by movement near volcanic provinces. Each quake is a small message from the interior. Together, they outline a body that still flexes and adjusts, a world that has settled but not stopped. The presence of such quakes matches the broader picture. A thickened crust under Tharsis, stresses frozen into rock, loads bending the lithosphere, and occasional slips relieving strain. As the tide shifts within the mind, it is easy to feel how height changes mood. On Earth, standing on a hill grants a small clarity. On Mars, A mountain that rises above weather sharpens that feeling into geology. At 22 kilometers above the plains, the summit lives where air is thin, frost is fleeting, and sunlight decides the daily script. Down the slopes, the basalt spreads in wide blankets, each one a quiet step in a long ascent. The Tharsis uplift gathers the scene into a single frame, with spokes of fracture pulling outward and companion volcanoes standing like distant kin. The facts hold close and steady. Low gravity helps a mountain grow tall. The lithosphere flexes and carries the load. Thin air sets sharp temperature cycles. Frost forms at dawn and vanishes in light. Basalt dominates. Water and heat can alter it. Tubes and pits suggest rooms below. Caldera terraces record the pulse of magma. Gravity and fractures map the buried architecture. Young flows show recent fire. Marsquakes whisper that the machine still turns. Another lantern appears as we think of our own daily cycles. We cool at night and warm with morning. Not as quickly as a Martian summit, yet with the same logic of radiation and rest. We store stresses and release them in steps, like caldera terraces forming one by one. We seek shelter when the surface feels harsh, and we value steady rooms when the world outside is sharp and bright. And still, the night continues, and the mountain stands above the passing clouds, a patient monument to simple reasons working for a long time. The next thought will drift toward how such heights influence winds and dust, and how even a thin atmosphere can carry stories across a wide plain. Jezero crater holds a picture written in rock, a lake's outline kept quietly intact. A river once entered from the northwest and slowed as it met standing water, releasing its load into a fan that spread and thickened. From orbit, that fan shows inverted channels where harder, cemented beds resisted erosion and now stand as ridges. Lobate margins bend outward along the delta's toes, a shape typical of sediment pushing into a basin. After touchdown, outcrops confirmed what the shapes suggested. Inclined crossbeds stack like steps, with foreset laminae dipping lakeward, each thin sheet laid during gradual advance. Graded beds appear where coarse grains settled first, and finer grains followed, a calm sorting in deeper, quieter water. Grain sizes fine away from the entry channel, moving from sands toward silt and mud as energy waned. These are the signatures of fluvial deposition, meeting a persistent lake rather than a brief, chaotic surge. As the tide shifts, ground-penetrating radar looks beneath the visible faces and traces the same story in echoes. Interfaces tilt and flatten exactly where a delta would prograde. Cliniforms step forward, then pause along erosional surfaces that mark retreats. Buried channel cuts bite into older beds before being filled by younger packages. Geometry above and geometry below align, pointing to water that lingered long enough to lay down order. Mineralogy adds the color tones to this scene. Fine-grained mudstones and siltstones contain clay minerals that form in neutral to mildly alkaline waters, not in harshly acidic pools. Such waters help preserve delicate organic molecules by limiting breakdown and allowing adsorption onto mineral surfaces. Along the crater margins, carbonate-bearing rocks indicate that water reacted with olivine-rich basalts, a path that fixes carbon into solid lattices. Those lattices can entomb organic fragments and hold them steady through time. In some higher sequences, sulfates appear, minerals that often follow evaporation as a lake shallows and concentrates dissolved ions. This upward move from clays and carbonates towards sulfates sketches a shift from fresher, longer-lived waters to more evaporative stages. Together, the minerals outline inflow, lake stability, chemical alteration, and final shoaling. Another lantern appears in this chain of evidence. When climate cooled and the atmosphere thinned, the water table likely fell. Channels incised into exposed surfaces, then later pulses refilled parts of the basin before the last retreat. The stone keeps the order of events without haste or embellishment. The search for organics inside this archive proceeds with care shaped by chemistry. Perchlorates in Martian soils can decompose organics when heated, releasing oxygen that scrambles signals and creates false positives. Instruments therefore follow stepwise protocols that minimize thermal damage. Gentle extraction methods try to coax compounds off mineral surfaces before higher temperature steps are used. Spectrometers compare wavelengths absorbed or emitted by molecules, while chromatograph, two mass spectrometers, separate mixtures and weigh fragments to build fingerprints. Cross-checks between instruments help discriminate true organics from artifacts. Where evidence seems promising yet ambiguous, the rover stores cores in sealed tubes, keeping a clean chain for eventual return to Earth. Laboratories at home can apply techniques not possible inside a rover body, including isotopic measurements that resolve subtle fractionations and structural analyses that trace complex macromolecules. Even then, organics alone will not declare a life story. Geology makes organics too, through serpentinization and impact synthesis and UV-driven reactions. Context is essential. Structures that repeat in biological ways, patterns linked to cell-size spaces, or isotopic ratios that favor lighter carbon in specific compounds. These converging signs would carry more weight than any single detection. In this calm approach, hope stays present but disciplined, as a hand resting on a steady rail while crossing a narrow bridge. Sediments hold time in their layering. Valve-like laminations, if continuous and fine, could record seasonal cycles or episodic inflow changes as dust storms rose and waned. Faint couplets of lighter and darker laminae might reflect shifts in grain size or mineral input across repeating intervals. Embedded pebbles, drop-like and scattered, mark moments when flow quickened, perhaps during channel avulsions or storm-fed surges. Rip-up clasts torn flakes of earlier mud signal, a pulse strong enough to erode a soft bed and redeposit those pieces downstream. Distinct packages bounded by sharp surfaces imply lake-level falls when channels incised, followed by refilling that draped new layers over the scoured floor. These cycles can resonate with climate drivers that act in known rhythms. Orbital variations adjust where sunlight lands and how much warmth lingers through a year. A thicker or thinner atmosphere shifts pressure, alters boiling points, and influences whether liquid water can persist at the surface or must hide in pores and fractures. Water reservoirs at the poles and in the subsurface store and release moisture as conditions change, feeding or starving inflow. In this grammar, each lamina, bed, and boundary is a clause placed with purpose. And still, the night continues, and the rock holds the conversation exactly as it was spoken. Standing before these outcrops, the distances in space and time feel less severe. A delta's forceps are familiar to anyone who has watched a stream slow and fan into a pond. A graded bed resembles the way we settle after a long day, larger worries sinking first, finer thoughts drifting down after. Yet the facts remain in front, clear and quiet. A channel entered, a lake accepted its burden, sediments sorted by energy, and minerals recorded the water's chemistry. Subsurface radar traced cliniforms that marched forward, paused, and advanced again. Carbonates formed along margins where water met basalt and fixed carbon into stone. Sulfates rose higher in the stack as evaporation gained influence. Instruments tempered by the presence of perchlorates tested for organics with caution and cross-checks. Samples were sealed for patient study beyond the rover's reach. Laminations, pebbles, and clasts marked rhythms of flow, fall, and return. These are simple statements that carry weight because they fit together without strain. As another page turns in the lake's stone diary, the message is not dramatic. It says only that water stayed, that it moved with seasons and longer beats, and that the basin remembered. What this teaches feels close to home. Stability is often not a single state, but a sequence of adjustments, each layer resting on the last. A lake deepens, shoals, and steps back. A climate loosens its grip, then tightens again. We do something similar with our days, storing what matters in steady places, letting excess evaporate, and returning to the calm that preserves meaning. The Jezero record shows that patience is not empty time. It is accumulation, gentle but decisive. As the last echoes pass through the radar field and settle into curves on a screen, the shape of a long-lived lake stands out, neither guessed nor insisted upon, but simply observed. The trail forward drifts toward what those pages might hold about chemistry that lingered with care, and whether patterns in carbon, structure, and isotopes will one day lean together in the right direction. For now, the lake written in stone is enough to rest beside. Its sentences short, its cadence slow, its facts like quiet lights across a wide surface. Beneath the dusty mantles and the quiet volcanic plains, instruments whisper of brightness coming back from the dark. Radar pulses slip into the ground and return with strong, sharp echoes, the kind that fade only a little with depth, a signature that matches water ice more than stone or compacted dust. In the mid-latitudes, long lobes sweep out from slopes, their surfaces rucked and banded, the shapes we know from glaciers on Earth. Flow lines bow gently around hidden obstacles. Ridges fringe their margins like softened moraines. The rubble above is a mask, but the relief underneath keeps its glacial grammar. Even where the equator's influence warms the afternoons, orbital data speak of thicker bodies than anyone expected, stacked in formations once treated as nothing but wind-built dust. Their layers run for kilometers in thickness, and their measured dielectric constants point again toward ice-rich strata, not merely hardened silt. The facts suggest a different climate past, a time when snow or hoarfrost reached far from the poles, settled quietly, and then was buried by dust that sealed it from the thinning air. As the tide shifts in an invisible ocean of time, the importance of this hidden cold becomes plain. Ice, buried at depth, preserves a ledger of humidity, temperature, and pressure, because stability demands a careful balance of these things. If ice persists at latitudes that now feel comparatively warm, then the planet once tilted differently, or breathed a denser atmosphere. Mars's axial tilt is not locked, it wanders. Models of the planet's chaotic obliquity show swings over hundreds of thousands to millions of years, shifting the places where frost remains and where it vanishes. When the tilt grows, the cold traps drift toward the equator, and volatiles resort across the map. Radar-mapped reflectors, stacked like pages, can stand in for those cycles, count the bright interfaces, match them to dated surfaces or to crater counts nearby. And a fine paleoclimate curve begins to emerge, not drawn in ink but in ice. Each layer becomes a season in the planet's longer memory, a measured pause in the migration of water through a thin sky. Another lantern appears when we think about people standing there someday. Shallow ice simplifies everything. Bringing water across interplanetary space is heavy work. Drilling a few meters rather than hundreds translates to less mass to launch, less power to spend, and fewer machines to maintain in dust and cold. But the ice is not distilled. Dust threads through it. Salts collect along lenses and boundaries. Mechanical strength changes from patch to patch, from brittle panes to crumbly mixtures. Landers have shown this plainly. Trenches scraped in the high latitudes revealed bright patches that faded over days as they sublimated into the air, proof of ice close to the surface. Lower down in latitude, the cover grows thicker or more cohesive, and access becomes a matter of excavation design, not just a spade in regolith. Heat the mixture and vapor will come, but perchlorates can travel with it, and those oxidizers matter for processing hardware and for the safety of crews. Any plan to drink the ground demands a partnership of geology and engineering. Survey before commitment, sample with care, test extraction methods at different temperatures and pressures, and design filters and scrubbers that handle salts without clogging or poisoning systems meant to protect lungs and skin. And still, the night continues in the present cycle, which has not stopped while we look back. Water vapor migrates with the seasons, settling as frost before dawn and lifting as the sun returns. Ice clouds thinly sail the high atmosphere, tracing circulation patterns from valley to volcano. Sublimation rates depend on gradients that are simple to state and careful to handle. If temperature rises and the path to the air is open, loss quickens. If a dust blanket rests above the ice, even just millimeters thick, the escape slows dramatically. Impacts expose fresh ice where small craters punch through the cover. Mass wasting peels back scarps to reveal blue-white bands that brighten in new light and then dim as they retreat again from the open sky. The buried cold is not inert. It exchanges with the air, but at a pace that honors the protection of dust and the shadings of slope and aspect. As a string laid in a loop can show the shape of an orbit, these instruments outline reservoirs hidden beneath footsteps of dust. Ground-penetrating radar draws the interfaces in long, continuous strokes. Neutron spectrometers listen for hydrogen enrichment and map it as gentle gradients, telling where ice is likely and where it is not. Cameras catch brief glints where new exposures appear, confirm angles of layering, and track the parts that change with each season. The combined signals make a map that does not promise seas and does not need to. It proves there is a distributed archive, stored in silence, that can be read and carefully tapped. A softer breath moves through the idea when we return to the climate story. Ice preserved away from the poles insists on past intervals when tilt and air pressure allowed stabilization far from today's cold sinks. Simple, rounded timescales help the mind hold it. A few 100,000 years for shorter swings, several million for the deeper beats. Between them, dust storms thickened the skies, albedo shifted, and frost lines advanced or retreated. Layered deposits record that motion like chords, repeating with variation. When two records agree, the radar pages and the visible terraces, the hydrogen maps and the crater counts, the confidence grows. Tie points then allow correlation across basins and plateaus, and a planet-wide rhythm starts to resolve. The science remains cautious, because calibration still needs footholds, but the method is sound. Let the ice be the chronometer when rock alone feels silent. As the wind turns a page, the human thread returns. The logistics of living with buried ice ask for patience and redundancy. Prospect first with remote sensing, then ground truth, with drills that sample without thawing, then decide how to heat, trap, and clean the vapor. Work in shade where possible to slow losses. Keep excavation slopes gentle to resist collapse in low gravity. Store water in tanks that can radiate heat when needed and insulate when not. Treat every kilogram as precious, because every kilogram was hard-won. Plan for the chemistry that reality provides, not the purity anyone would prefer. The rhythm here mirrors daily life anywhere. Understand the place, accept its texture, and design around its stubbornness. A final note gathers the threads without raising the voice. The buried cold is both memory and resource. It tells us when the sky was thicker and the tilt was greater, when frost walked farther from the poles and chose to stay. It offers stored water that may be reachable with careful work, provided we respect its mixtures and guard against the hazards that travel with them. It continues to breathe with the season, slow and steady, changing a little each year, changing more across long stretches. We will only see through instruments and inference. Like a quiet attic where family letters rest, these deposits hold the record and the means for a future visit, written in layers that do not boast, merely endure. And somewhere beneath the next dusty ridge, another bright echo waits, answering softly when called, reminding us that the planet keeps its promises in ice. The surface of Mars wears its color like a memory. Every shade of red, from soft rose to iron rust, comes from chemistry written in its dust. Iron in the basalt meets a whisper of oxygen and changes state its electrons rearrange, catching sunlight differently. Nanophase ferric oxides, born from slow weathering under scarce water, coat grains as thin as breath. The result is a planet that glows, not with heat, but with oxidation. Fresh bedrock is darker, closer to charcoal than fire. When a rover drills into stone, the shavings below the surface gleam gray or black, untouched by air until that moment. The difference between crust and core is time made visible, a quiet record of how long the planet has been exposed to wind, frost, and light. Under every camera's gaze, spectra speak a simple language. Volcanic minerals such as olivine, pyroxene, and plagioclase, altered into clays, hematite, and sulfates. In some regions, the hematite forms perfect little spheres, scattered like berries in sand. Scientists call them concretions. Rovers once called them blueberries. They are iron stones formed in pores of ancient rock where water once passed, oxidizing and precipitating until they grew smooth and round. Each one marks the ghost of a wet moment, like raindrops that hardened instead of falling. Around them, gray mudstones and fractured veins hint at groundwater that moved, paused, and moved again, shaping chemistry the way tides shape shores. Other discoveries lie less in color and more in reaction. Perchlorate salts, found by multiple missions in soil and dust, form through ultraviolet light and the planet's thin photochemical air. They complicate the search for organics, breaking molecules apart when heated. Yet they also change the rules for water, letting salty brines stay liquid for a while at temperatures where pure water would freeze solid. Laboratory work and field analogs on Earth test these thresholds, finding that under the right humidity, microscopic films of brine could shimmer briefly before the dry, cold winds again. On Mars today, such moments would be fleeting, measured in minutes, not days but beneath the surface. In pores shielded from sunlight and wind, liquid could linger longer, hidden in grains and salts. Gale craters' layered rocks tell another chemical story. There, hydrated silica and opaline coatings record long interactions with water at low temperatures, where minerals dissolve and reform slowly. On Earth, similar silica can preserve fine details of life, microtextures, fragile filaments, the shapes of cells themselves. On Mars, no proof of life lies within, only the potential of preservation. Carbonate veins in certain ridges show that carbon dioxide-rich water once met basalt and left behind pale traces of reaction. These minerals capture part of the planet's lost atmosphere, the same gas that now drifts thin and cold above. Their presence confirms that chemistry and climate have always been partners, trading carbon between sky and stone. Some layers tell of drying, not flow. Sulfate-rich beds, bleached and brittle, point to evaporation and acidity, to lakes that grew shallow and harsh as time moved forward. Even these are clues to endurance. For a while, water stood, then receded, and the minerals that remained hardened into pages the wind could not tear. The record shows transition rather than absence, an evolution from neutral lakes to briny pools to dust-choked basins, each narrowing the window for habitability without closing it completely. Radiation threads through all these reactions. Without a magnetic field to deflect cosmic rays, high-energy particles strike the surface every day. They split molecules, rearrange bonds, and erase delicate organics near the skin of the soil. In deeper layers, a few centimeters below, the damage lessens. At decimeters, traces may persist for millions of years. That is why drills dig carefully, reaching just far enough to hide from the sun's reach. Samples sealed for future return. Hold more than rock, they hold time at different depths, chemistry stored at different stages of exposure. Over epochs, the radiation that fades color on Earth here turns color into permanence, a planet painted by physics as much as by iron. When light from the sun reaches this world, it does not scatter evenly. Red wavelengths reflect best, painting the thin air and the dust in warm tones, even when temperatures stay below freezing. From orbit, that hue becomes a symbol of distance and endurance. Up close, it is granular, made of particles too fine to see, each one a small oxide that once tasted air. The color of Mars is not decoration, it is process. Oxidation speaks of time, of water lost, of minerals changed and frozen in place. It reminds us that even in silence, transformation continues. And still, beneath that red veil, chemistry whispers possibilities. Clays recall gentle waters, sulfates remember their final drying, carbonates record a meeting between gas and rock. Silica glints faintly where fluid lingered long enough to alter but not destroy. Radiation hums its steady tune, the pulse of space pressing against the ground. The planet endures, its skin a map of reactions that never truly stopped. To look upon it is to see what patience does to matter, how iron learns to hold sunlight, and how a color becomes a memory no wind can erase. A breathless quiet rests above Mars, where the air is thinner than a whisper and the shield between world and space is barely there. Over eons, that frail veil has changed the planet's fate. Spacecraft that circle and listen have traced the ways its atmosphere escapes, through ion pickup, through sputtering, through the constant brush of the solar wind. High above the red plains, charged particles from the sun strike the upper air, stealing atoms and sending them drifting into interplanetary darkness. Hydrogen, the lightest, slips away most easily, often born from water vapor split by sunlight. Oxygen lingers longer, bound by gravity for a time, but even heavier gases find slow routes outward. Each loss is small, yet the losses add up, soul by soul, century by century, until the sky thins beyond repair. Long ago, the story was different. Buried in crustal rocks are tiny magnetic traces, leftovers of a field that once wrapped the planet. That remnant magnetization tells of a time when a dynamo churned within a liquid core, spinning out a global field that deflected the solar wind. As the core cooled, convection slowed, and the dynamo faltered, the field faded like an ember, losing heat. Without that magnetic cocoon, the atmosphere stood exposed to solar stripping. Molecule by molecule, the air escaped, and the greenhouse warmth weakened. The world cooled, water froze or fled. Valleys that once ran with liquid began to dry, leaving only the geometry of flow carved into stone. It was not a single moment, but a slow unspooling, the transformation of a world that once could hold its breath into one that could not. As the night of history deepened, radiation took its place among the planet's permanent guests. At the surface, galactic cosmic rays arrive from distant stars, their intensity modulated by the sun's rhythm. Solar energetic particles brief, fierce storms of radiation sometimes sweep past, altering the dose by orders of magnitude for hours or days. Rovers and orbiters, carrying delicate detectors, measure the invisible flux. The numbers vary with altitude, with the thinness of the air above, and with the shielding offered by rock or hull. During global dust storms, when sunlight warms the air and causes it to expand, the atmospheric column thickens slightly. Shielding improves, and the background radiation softens. In clear, cold seasons, when the air contracts and pressure falls, the opposite occurs. Even in such difference, the air remains too thin to provide comfort. To its protection is measurable, but never complete. For future travelers, that thinness demands care. Habitat walls will need to turn radiation into a manageable companion rather than a threat. A meter of local regolith piled overhead can cut the exposure dramatically, transforming raw space into something survivable. Lava tubes and natural caverns may serve even better, the ancient bones of volcanoes now offering shelter. Electronics face their own hazards. Their circuits tire under constant bombardment. Redundant systems, hardened components, and careful timing. These are the quiet forms of patience that keep machines alive, where storms of particles never fully cease. Under the pale sky, ultraviolet light reaches further down than on Earth. The air is too thin to filter it. It strikes dust and rock, drives the creation of oxidants like peroxides and perchlorates, and splits fragile molecules apart. The chemistry it stirs helps explain why Martian soil is so reactive, why landers found oxidizing compounds instead of organic comfort. For scientists seeking traces of ancient biology, this photochemical harshness is both clue and obstacle. Samples must be handled gently, shaded, sealed, kept from the same light that has already erased so much. The air's touch is not kind to materials either. Temperature swings of more than 100 degrees can come between afternoon and dawn, stretching and shrinking metals, seals, and composites. Dust, fine, as smoke seeps into joints and fabrics, abrades surfaces, dulls optics. Each sol brings a cycle of expansion and contraction, breathing through instruments and habitats alike. In such rhythms, wear accumulates like wind-polished stone, a slow reminder of the environment's persistence. Yet even here, the thin shield is not static. It moves and breathes. In the Great Basin of Hellas, the deepest point on Mars, air pressure is slightly higher enough to alter how water boils and how wind curls across the floor. Seasonal carbon dioxide caps at the poles grow and shrink with sunlight, locking and releasing tens of trillions of kilograms of gas each year. As CO2 freezes out in winter, global pressure falls. As it sublimates back in spring, the atmosphere swells again. The total swing can reach about a quarter of the mean pressure, an entire planet inhaling and exhaling once per year. These pressure tides ripple into weather, shaping jets aloft, stirring dust devils on plains, driving cold air down volcanic slopes at night. Even through its fragility, the atmosphere remains a storyteller. It records time not in rain or river, but in shifting frost and fading haze. Clouds rise over volcanoes at dawn, dust streaks trace unseen winds, and carbon dioxide frost sketches the rhythm of seasons. The shield may be thin, but it is alive with motion, bending light, carrying heat, breathing in and out beneath the cold stars. To study it is to glimpse both what Mars has lost and what it still keeps, the faint breath of a planet that endures its exposure with quiet grace. And as the night continues, that breath becomes a reminder. Even a thin veil can hold meaning, and even a small world can keep its story in the air that remains. When dawn breaks on Mars, it does so quietly. The horizon lightens, thin and rust-colored, and the machines stir. They wake within margins of energy and temperature so narrow that each watt and degree becomes a line between rest and survival. Solar-powered rovers wait for their panels to drink in light again, their systems measuring how much dust has gathered overnight. If the panels are clean, power flows quickly. If coated in the planet's fine powder, energy must be rationed, heaters paused, instruments silenced. Those that run on nuclear warmth, small radioisotope generators, glowing unseen within their shells, breathe more steadily. Their hearts never cool, their pulse constant. Yet even they must portion their output carefully between motion, analysis, and heat. Every subsystem waits its turn, balanced within equations as delicate as frost. On Earth, engineers watch the morning begin on another world. They have already sent the day's plan, built from maps, images, and science priorities. The rovers move according to those instructions, line by line, as sunlight climbs. Cameras survey the plain, reading the texture of rock and shadow. By night, the gathered data returns through orbiters circling above, then across the vast deep space network to antennas under Earth's own dawn. The rhythm continues. Think on Earth, act on Mars, receive in darkness, and think again. Each soul adds a stanza to that distant choreography. The eyes of these travelers are many. Mast-mounted imagers gaze far across the landscape, tracing ridges, dust plumes, and the tilt of outcrops. Close to the surface, hand-lens cameras reveal the fine textures of sediment, the laminations of once wet layers. Lasers strike at chosen spots, vaporizing a grain to read its elemental glow. The faint plasma, measured in split seconds, tells of silicon, iron, calcium fragments of a planet's story compressed in light. Deeper still, X-ray diffraction instruments unravel crystal lattices, distinguishing clay from carbonate, sulfate from silicate. Each distinction is quiet but profound, each one marking where water touched rock, where chemistry once lingered in balance. Other sensors look beneath. Ground-penetrating radar slips signals into the soil, reading the echoes that come back from buried layers. Weather stations count the rise and fall of pressure, track temperature, humidity, and wind. Radiation detectors tick gently in the background, keeping time with cosmic rays. None of these tools alone can tell the whole story, but together they triangulate the truth of habitability, whether water once pooled here, what minerals formed in its absence, and whether organic matter could have survived the thin, fierce light. Movement itself is a kind of observation. To drive across a basin or up a ridge is to sample different epochs of stone. Each traverse crosses boundaries, invisible at first lines where chemistry, texture, or color shifts. Wheels and suspension absorb the unevenness, designed to withstand sharp basalt, soft sand, and the rhythmic roll of ripples. Yet limits remain. Slopes above 20 degrees demand caution. Ripple fields can swallow momentum, and fine dust can cling to treads like memory. Navigation software builds three-dimensional meshes from stereo images, planning paths that avoid shadowed hollows or steep lips. Autonomy grants each rover a measure of self-trust, allowing it to choose safe steps within a pre-drawn corridor, maximizing distance in the short Martian day. At certain stops, the drills awaken. They sink slowly, turning powder into knowledge. Ground samples fall into tiny sieves, and portions measured in grams find their way to miniature laboratories within. Some cores are sealed entirely, cached for hands that may come years or decades later. Each receives a serial mark, a coordinate, a record of where and when it was taken. The archive builds not in shelves, but in titanium tubes, resting in the dust. Communication links hold all of this together. Relay orbiters, when geometry allows, beam gigabits of science home in brief, precious sessions. Between passes, the rovers keep to themselves, storing data in silence. Sometimes, a direct link to Earth continues a faint whisper of telemetry, the minimum heartbeat that confirms all is well. But when the sun slides between the two planets, everything must rest. For those few weeks of solar conjunction, commands pause. The machines follow their pre-written routines, weather logs, still frames, instrument checks, until the bright interference fades and the link clears once more. Dust storms bring another kind of waiting. As the sky thickens, light drops, panels darken, temperatures fall. But aloft, sunlight scatters and warms the higher air, shifting pressure and wind patterns. The balance changes. Engineers on Earth watch tau values rise and send careful sequences, lower power draw, selective heating, reduced motion. Systems sleep in safety until the storm thins. Then, slowly, light returns, and the machines wake, cautious but ready. Their survival is a negotiation between patience and preparation, an understanding written into code and alloy. To call these explorers awake is more than poetry. Their sensors know dawn, their heaters sense dusk. Each soul, they align themselves with the planet's rotation. Their clocks, set not to Earth's 24 hours, but to Mars's slightly longer rhythm, 24 hours and 39 minutes. It is a different tempo, one that human teams adopt in cycles, living out of sync with their own Sunday. The rovers and landers follow it with precision, waking in chill light, working until evening frost, resting through the deep cold night. Their awareness is mechanical, yet in it there lies a quiet resemblance to life, a pulse of warmth, a memory of motion, a steady watch for morning. As the red horizon glows once more, they begin again, faithful to the same dance: think, act, wait, and wake. From stereo eyes in orbit, the surface unfolds in contours of height and echo. Two images taken from slightly different paths become a pair for parallax, letting software trace elevation by comparing how shadows shift and edges align. With enough overlap, the result is a digital relief, every dune and crater given gentle measure. When orbiters spread this process across the planet, a quiet dichotomy emerges. Southern highlands, older and bruised with craters, and northern plains, smoother and lower, where the past may have carried seas or wide lava sheets. Between them lies a sharp, uncertain boundary, one of the deepest questions of Martian geology, suggesting either the scar of an ancient impact or a slow reshaping from within. When the mantle stirred unevenly and tilted the face of a world, laser altimeters sweep the globe like steady metronomes. From each pass, pulses travel down, strike the surface, and return within billionths of a second. Range becomes height, and height becomes pattern. Over many orbits, the data cross-link into a grid so exact that mountains and basins acquire definition finer than human-made maps of early Earth. This topography is both memory and measure, a record of where the crust thickened and where it sank, of how later flows filled the lowlands and winds wore down the highs. As the tide shifts, the canyons come into view, their walls receding in quiet stairways. In Valles Marineris, stereo reconstructions reveal a depth of kilometers, with layers folded like pages in a massive geological book. Within them, alternating tones and rhythms suggest periods of deposition, intervals when dust or ash settled, then hardened in time. Some layers may be volcanic, others sedimentary, each testifying to moments when water or air laid down its trace before retreating. The benches and cliffs repeat like verses of a long, deliberate poem written in stone. Beyond the canyons, channels stretch outward toward the northern plains. Kasay, Aris, and Shalbatana cut wide, branching paths as though carved in haste by massive floods. Streamlined islands and grooved floors show the mark of momentum far beyond the trickle of today. The cause is uncertain, but likely sudden, perhaps volcanic heat, releasing subsurface ice, or pressure rupturing aquifers. The water would have raced downslope, carrying boulders and sediment, until it slowed, spreading into the basins and leaving vast fans where plains begin. These forms remain untouched now, but they keep the memory of liquid energy that once ran free beneath the same thin sky. Another lantern appears with radar, whose eyes see through dust and cover. Instruments send chirped signals downward, their echoes rebounding from hidden boundaries, ice over rock, layer over layer, or voids packed with different minerals. At the poles, bright reflections trace stacks of ice and dust built in cycles, each sheet marking a shift in climate driven by orbital rhythms. Outside those frozen caps, radar returns reveal debris-covered glaciers, curled within valleys, their internal ice shielded by rubble. In equatorial zones, certain plateaus echo like ice-rich bodies buried beneath a dry crust, suggesting that the planet still hides reservoirs in shadow and depth. Each echo invites a pause, a reconsideration of where water went and how it might yet linger. High-resolution images weave all these senses together. Cameras capable of resolving about 25 centimeters per pixel record, landscapes detailed enough to show rover tracks, wheel marks, and the glint of hardware resting in the dust. Small impacts appear as fresh scars, and the repetition of scenes over months captures change. Slopes shifting, dunes migrating, cliffs releasing small avalanches of dust. The map becomes dynamic, not only a record of height, but of time, a living atlas refreshed with each pass of the orbit. When rovers plan their paths, they move across this layered knowledge. Each coordinate is more than a number. It carries elevation from the laser, depth from radar, and texture from light. Engineers trace routes across contours, through plains shaped by echoes, and through valleys drawn from stereo views. Every meter forward becomes a dialogue between image and instrument, between memory and motion. The map is no longer flat, it breathes, it reflects, it remembers. And still, the night continues, soft and red around the planet's curve. The geography written in these numbers is not cold abstraction, but a portrait of endurance. Heights whisper of uplift and loss, echoes tell of buried ice and vanished flow. Together they compose a map, made not only of terrain, but of time, an atlas of patience, measured by light and returned in silence, where even absence leaves a trace for those who listen. Sedimentary rocks hold stories that flow and settle, recording the language of water in fine detail. Within the delta, every layer remembers motion. Cross strata lean gently in the direction of past currents, like pages tilted by a breeze. Their dipping angles reveal how the flow once turned and slowed. Each foreset slope shows the balance between gravity and resistance, telling how steep the sediment could rest before it slipped again. The grains themselves arranged by strength and calmness. Coarser bands speak of floods, when energy was high and channels surged. Finer laminae whisper of still water and long pauses. Under magnification, the grains hold their own travelogues, edges scuffed and rounded by abrasion, or smoothed chemically in quiet pools. From these textures, one can sense how far they journeyed and from what rocks they began. Buried between them, fragments of organics wait. Their survival depends on how quickly the next layer arrived and what minerals surrounded them. Clays can fold molecules into their interlayers, locking them away from oxygen. Carbonates can form in an instant, entombing biofilms in crystal. Silica can coat shapes, freezing outlines before decay. Each path of preservation has its own narrow window of temperature, of pH, of timing. It is a quiet chemistry that chooses what the future will remember. The Martian delta's fine print lies in these conditions, the unspoken rules that decide what remains after eons of dust and cold. To read that print, instruments must behave like patient hands. Onboard analyses begin gently, warming samples only to mild heat at first, to release volatile organics without destroying them. Later, higher temperatures follow, step by step, coaxing deeper compounds from the matrix. Derivatization agents convert stubborn, non-volatile molecules into vapors the detectors can measure. Mineral maps from X-ray diffraction guide every stage, alerting when oxidants or reactive clays might burn delicate traces. Isotopic ratios add another whisper of meaning. Slight shifts in carbon or sulfur masses can hint at biological fractionation, the way living systems prefer lighter isotopes. But nature can imitate life. Rocks can mimic the same pattern through purely chemical paths. Ambiguity is not failure. It is caution shaped into method. That is why cores and fragments are stored carefully, sealed for laboratories on Earth that hold instruments 1,000 times more sensitive. There, each molecule can be tested, its structure unrolled and compared, until what seemed uncertain gains its proper clarity. The delta's architecture also tells how long its lake endured. When sediment builds outward in steady layers, aggradation implies continuous inflow, the lake maintained by stable climates. When surfaces are cut and channels incised, drawdowns are implied periods when water fell and rivers sliced back through their own deposits. Around the crater rim, benches and terraces mark old shorelines, steps around a vanished sea. If those levels match the delta's elevation, the geometry becomes a calendar. The minerals within confirm the setting. Iron-bearing clays, mild carbonates, minerals that form only in neutral or gently alkaline water. Later, higher beds show sulfates, crystallized from evaporating brines. Together they trace an arc from abundance to desiccation, a climate drying, step by step, under a thinner and colder sky. To interpret such forms, scientists look to Earth's mirrors. In arid basins here, deltas grow much the same mouthbars, giving way to quiet prodelta muds as currents lose speed. Subsurface radars on Earth reveal the same gentle clinoforms that Martian rovers see in miniature, bedding that tilts and repeats. The resemblance is not identity, it is physics translated through difference. Mars had no dense air to slow grains, no forests to bind channels, and colder nights to freeze flows. Yet water followed the same rules. It spread where energy dropped, deposited by weight and size. Small particles stayed suspended until calm returned, then settled in order, one atop another. Even under alien light, these laws held constant. The fine print of the delta is written in those laws of gravity, current, and time. If there is any trace of life in such a record, it must fit within that structure. It cannot float outside the sediment's logic. Biology, if it ever touched this place, would appear as a subtle variation, a shift in isotopes, a cluster of preserved organics, a texture within a mineral crust. The story cannot skip its lines. It must align with physics and chemistry, grain by grain. That restraint gives the search its depth. Certainty grows not from imagination but from repetition, from the patient matching of layers and spectra and signs until every whisper agrees. As the night of the planet turns, dust moves softly across these stones. The delta waits, holding its instructions beneath a pale crust. Its language is precise, composed of angles, grains, and bonds. To read it is to accept slowness, to let small details speak. And as on Earth, where rivers inscribe their memory into clay, the delta's quiet architecture becomes both archive and mirror, showing how motion becomes rest, how energy turns to pattern, and how even silence may keep the shape of a vanished current. At pre-dawn, when shadows lie long and still, the air thins above Mars's great volcanoes. Temperatures sink sharply with height, and along those colossal slopes the rising air cools as it climbs. The process is quiet and predictable, adiabatic cooling, where expansion drains warmth until invisible vapor reaches its limit. Even on a planet so dry, the faint breath of water vapor can turn to ice. It gathers as frost on summit rims and in caldera hollows, forming a film only a few micrometers thick, yet broad enough to drape many square kilometers. Remote eyes in orbit see its shimmer and know its nature. At wavelengths near 1.5 and 2 micrometers, water absorbs light in ways that dust cannot, marking itself clearly in the spectrum. The frost is thin as breath on glass, but it holds a story of movement, of condensation and release. By sunrise, the surface warms beneath sunlight filtered through a cold sky. The frost sublimates, slipping directly from solid to vapor, folding its moisture back into the air. It drifts toward other shaded slopes or diffuses into the boundary layer, never still, never gone for long. This daily dance connects to the planet's deeper memory. The frost belongs not to the age of rivers and lakes, yet it obeys the same physics that once filled basins and carved deltas. Water still moves here, quietly, invisibly, tracing the lines of topography and season. Elsewhere beneath the surface, ground ice exchanges vapor with the air through pores in the dust. A thin protective cover, just a few centimeters thick, can preserve that ice for tens of thousands of years, slowing sublimation by orders of magnitude. Thermal models show how this insulation steadies the volatile balance, even at latitudes far from the poles. In some places, bright scarps retreat as ice beneath them vanishes, allowing cameras to measure the pace of loss and infer the depth of the frozen layer. Fresh impacts reveal blue-tinted patches that fade as they sublimate, their brightness a brief clock marking the time since exposure. The cycle continues, small but measurable, proof that water, though hidden, remains active in the Martian present. The frost's forgetfulness, its habit of vanishing, does not mean absence. Its comings and goings mark an exchange between reservoirs spread across the planet. The polar caps, the mid-latitude subsurface, and the lofty volcanic summits that briefly wear a sheen of ice. The data refine climate models, testing how humidity, temperature, and circulation interact with topography. Every dawn and dusk adds constraint to those maps of invisible flow. The frost also matters for future travelers. Transient moisture can influence dust adhesion, change static behavior, or affect how surfaces bond to machinery. Knowing where shallow ice lies beneath, regolith will guide drilling, anchoring, and construction. What forms and fades each morning becomes a kind of forecast for human hands to one day read. Other fleeting markings help calibrate its meaning. Dark slope streaks, which might once have hinted at water trickles, are now understood as dust avalanches cascading down steep walls. Seasonal frost, made not of water but of carbon dioxide, sculpts strange fans and spider shapes in the high latitudes. There, sunlight trapped under translucent slabs of CO2 builds pressure until gas jets erupt, carving channels beneath and scattering dark grains in branching patterns. The air is thin, the pressure low, yet sublimation remains an artist, etching and erasing landscapes through phase change. The water frost on the volcanoes is a gentler artist. It does not carve but settles and departs, rewriting its presence each day. It is phase change, made tender solid to vapor, vapor to solid, under the watch of a rising Sunday. As the night drifts toward dawn, the frost's rhythm mirrors something familiar. It appears pure and brief, then slips away before warmth can harm it. We too carry moments like this, small condensations of clarity that vanish when light returns but leave their trace in memory. The instruments remember what the surface forgets. Their readings turn passing frost into enduring data, into measurable proof that the planet still breathes in its own quiet way. Mars exhales vapor at sunrise and inhales it by dusk, a subtle respiration across millions of years. The frost forgets each morning, but the world remembers. And in that forgetting, in that daily disappearance, lies a continuity as gentle and precise as frost itself, thin yet certain, shaping the story of a living, shifting cold. Under the pull of a smaller planet, the body loosens in quiet increments. On Mars, gravity is only a little more than a third of what it is on Earth. Over time, that gentler pull lets the spine stretch by a few centimeters, easing the compression that constant weight once imposed. Muscles and bones, relieved of their daily burden, begin to thin unless they are asked to work. Exercise becomes a rhythm of survival, a ritual that keeps the body from forgetting how to stand strong. In every step, gravity writes softly into the bones, and when that handwriting weakens, the body must learn to trace it back by effort. Beyond the body's frame lies the constant whisper of radiation. The planet's thin air and absent magnetic field allow charged particles to fall more freely from the sun and the stars. Averaged over long stays, the dose rate rises beyond what Earth would ever give, and so walls must thicken. A meter of regolith, ordinary Martian soil can cut the dose in half. Shelters carved beneath the surface or hidden inside ancient lava tubes could give even more protection. There, the quiet is total, and the cold stone walls remember eruptions from millions of years ago. Every mission plan folds this arithmetic of shielding into its days and nights, balancing exposure and endurance like a slow heartbeat. As the light softens across the horizon, air itself becomes an enclosure. The atmosphere is too thin to breathe, too thin even to stand against pressure loss. Habitats must hold their own air, seal every joint, and watch for leaks the way a diver listens for a hiss beneath the sea. Water and air must circulate endlessly, drawn back from breath and waste, cleaned and renewed. Thermal swings, from bitter cold to sharp midday warmth, call for insulation thick and sure. Dust moves with every gust, creeping into seams, clinging to suits, testing filters and gaskets. Electrostatic brushes or vibrating membranes can shake it loose before it eats through cloth or metal. These are not speculative miracles. They are proven in principle, waiting only for scale and patience. Another quiet truth unfolds through resources. The air itself is heavy with carbon dioxide, a feedstock rather than a threat. Already, small laboratory units on Mars have split that gas into oxygen, producing a few grams each hour. Scaled with power, such systems could fill tanks for breathing or oxidizer for fuel. Ice buried under the surface, if melted and purified, could water crops and feed electrolysis for propellant. Salts and oxidants must be removed, but the chemistry is known. Energy will come from sun or core. Solar arrays will need cleaning after storms and storage for long nights, while compact reactors promise steadiness that ignores weather. Thermal control rests on how quickly the ground releases heat, how well the air can carry it away. Each landing site becomes a unique equation. Its soil, its latitude, its wind patterns, all combined to define what life can safely sustain. And still, the mind measures time differently. Communication with Earth stretches across the gulf, each message taking minutes to arrive, each reply arriving long after. Conversation cannot be live, it must be patient. At certain alignments, even that thread of light can vanish for days. In that distance, crews must hold together, managing precision tasks and private worries. The lessons come from years aboard the International Space Station, from simulations in Arctic huts and desert domes. Schedule with slack, allow quiet corners, rotate duties so monotony does not harden into fatigue. Prevent the small problems before they gather weight. Clean dust, sieves before they choke. Replace filters before air grows stale. Grease joints before they seize. Vigilance replaces heroics. The human measure is steadiness, not defiance. As the tide of thought drifts toward the surface again, the land itself dictates where life might rest. Scientists and engineers seek balance between discovery and survival. Close to sedimentary layers, the rocks hold records of ancient lakes and rivers, precious ground for studying past habitability. Yet operations demand shallower ice, flat plains, and low elevations for easier landing and greater atmospheric cushion. Even a small increase in pressure at lower altitudes helps slow descent and reduces fuel boil-off. Terrain must be kind enough for rovers to move, slopes gentle enough for construction. Hazards show themselves in dust storm frequency, in temperature extremes that stretch materials, in the soft traps of sand that wait for wheels. Every parameter has been mapped and measured through decades of orbiters and landers. Pressure curves, mineral spectra, and gravity gradients, all combined into the planet's quiet dossier. It is not a hostile world, only a precise one, unwilling to bend rules set by physics and time. As another lantern rises in the thin twilight, the image softens. Living on Mars is less about conquest than conversation. The planet does not yield easily, but it does not refuse. It asks for balance between strength and care, between machinery and mindfulness. Each habitat, each human heart, will adapt in kind. Spines will lengthen slightly, muscles will remember their work, and routines will fold into the rhythm of a world that turns a little slower. In that rhythm, under faint sunlight and patient dust, the human measure finds its place not as dominion, but as harmony, with a planet that listens only to those who move gently. The planet offers no comfort by default, yet it offers clarity. A day that lingers past hours by 40 minutes. An atmosphere so light that water must choose between ice and vapor. A sky that treats color differently at dusk, letting blue hold near the sun while red walks the horizon. Mountains higher than weather accumulate frost that forgets itself by morning. Beneath old flows and mantles lie archives of ice measured by echoes, aligned in layers like pages pressed by time. In a crater that kept a lake, deltas record the angle of ancient currents, and fine mudstones lock away grains that once settled in calm water. When instruments are careful, the chemistry speaks plainly. Clays where neutral water lingered, sulfates where drying advanced, carbonates where basalt met carbon dioxide, silica where fluids altered slowly and preserved. These are not ornaments. They are the structure of a world that slowed enough to become readable. The thin shield of air cannot keep everything it once held, so the ground wrote it down in minerals and shapes, in the width of channels and the tilt of forceps. Radiation lines the margins of possibility and teaches where to look for preserved clues within rock, below dust, away from the harshest light. Rovers wake, work and sleep by power budgets that respect cold mornings and warm afternoons. Their data return to fill maps made from heights and echoes, so that every decision carries coordinates, context, and consequence. When we imagine walking there, we do not promise what stone cannot promise. We keep to facts and add careful hypotheses. Ice at reachable depths in some regions, oxygen from carbon dioxide with enough power, shelter built under regolith, where rays fade and temperatures calm. The human story would have to match the terrain's patience, trading hurry for endurance, spectacle for maintenance, and grand claims for quiet verifications that accumulate until they mean something sure. Sleep with the sense of a slower evening, an extra drift between tasks that the soul itself allows. Think of dust choosing blue near the sun, and of frost that appears without announcement and leaves without trace. Think of a delta that knows more than we do and keeps it safely in layers waiting for tools that read gently. The universe does not rush. This neighboring world shows how knowledge grows when motion slows. Let that rhythm steady your breathing. Let the measured facts keep you company like distant lights that never flicker. And let the long night be friendly while another morning forms on a red horizon far away.